So in this synthesis, we're asked to use 2-butanone as the only source of carbon to form Z2-butene, which is also 4 carbons. So there are actually 2 pathways for this reaction that specifically give us the Z-alkene. One way is to use Lin-Large catalyst at some point, which gives us this cis configuration. So to use Lin-Large catalyst, we need the alkyne, which is the substrate for that reagent. And to form the alkyne, some sort of elimination reaction can be used. So for example, if we have this compound here, and we have 2 halides coming off of carbons 2 and 3, we could carry out a double elimination where the electrons flow into carbons 2 and 3 from both carbon to halide bonds. That's what's called a double elimination. So let's see if we can form this compound here, the vicinal dihalide, from the carbonyl that was given to us. Forming a vicinal dihalide like here requires an alkene, if that's the path that we choose. So we could form the transalkene and react this with bromine in dichloromethane. And that is actually an electrophilic addition where this pi bond is the nucleophile and here's our electrophile. So let's see if we can form the transalkene and then modify it to form the cis-alkene. Now to start, we need to remove this carbonyl on 2-butanone and form the alkene between carbons 2 and 3. So one way to do that is to first turn this into an alcohol, like so. And we know alcohols are susceptible to dehydration reactions, so eventually we can take the alcohol, dehydrate it, and form this alkene here, specifically trans. So if we observe our carbonyl and our alcohol, we can see an introduction of 2 hydrogens, one located right here, which is bound to the oxygen, and another one which isn't shown right here. So the addition of hydrogens is a reduction. And to reduce this ketone, we can use sodium borohydride reducing agent. And the solvent for this reaction is ethanol and water. After we reduce it, we can dehydrate. And one way to do that is by using sulfuric acid and setting the reaction to about 160 degrees. And it's these vigorous conditions that allow us to form the Zaitsev product, the trans-2-butene. So now that we have this trans-alkene, we need to go to the cis-alkene, and we said we need to do that with an alkyne intermediate. So essentially what we need to do is convert our alkene into a vicinal dihalide, which can then be formed into an alkyne, like so, and then finally our cis-alkene. So we have 3 steps to accomplish. Now to form the vicinal dihalide, we can use Br2 and dichloromethane, which reacts with our alkene in an electrophilic addition reaction. And with our vicinal dihalide, we can react it with 2 moles of sodium amide base, which is dissolved in liquid ammonia. Let's call our alkyne compound 1. We take that and react it with Lin-Large catalyst to form the cis-alkene. But what if we use carbonyl reactions? After all, we are given a carbonyl. So one clue is using the Vinegar reaction, where we have a 2-carbon component being contributed by a carbonyl and another 2-carbon component being contributed by an alkyl halide. If the stability of that phosphonium ylide leans towards reactivity, unstable, we can form the cis-alkene here as long as we have our components. So if we just observe what we're given, which is 2-butanone, and we're asked to form our cis-alkene, the carbon count is conserved, where we have 4 carbons here and 4 here. But in order to carry out a Vinegar reaction such that we form the cis-alkene, we need a 2-carbon aldehyde and a 2-carbon alkyl halide. Now one way to form our components is to convert this ketone into an ester using Baeyer-Villiger. And we know esters are perfect substrates to chop up, to hydrolyze into 2 separate 2-carbon components. So let's carry out the Baeyer-Vinegar reaction, where we take our ketone and react it with MCPBA in a polar aprotic solvent. And just like in the previous example, the oxygen is sandwiched on the more highly substituted side. So in this case, it takes preference towards the secondary carbon, and in the process, it inserts the oxygen at that position. So now we have an ester. We have ethyl acetate. And our ester is a perfect substrate to be hydrolyzed as an acyl compound. So we can do an acid or base hydrolysis. Let's use acid. And what that does is form acetic acid and ethanol. And now the path from here is pretty straightforward. As soon as we chop up the ester, we now have 2 carbon components, which are our substrates for the Vinegar reaction. We still need to make some minor adjustments. The Vinegar reaction requires a carbonyl. So to convert acetic acid into acetaldehyde, which looks like this, we can react it with dibol. So as an acyl compound, acetic acid is susceptible to reduction, but dibol in specific is a weak reducing agent. So it stops the reduction at the aldehyde and not the alcohol. And just like lithium aluminum hydride, we need an aprotic solvent, which is also polar and very low temperature. And in the second step, we quench it with aqueous hydrochloric acid, which is our aqueous workup. Now we need to modify ethanol. So we can take ethanol and form bromoethane, which is our second component of the Vinegar reaction. And to do that, we can react it with PBr3 in pyridine and toluene. Now we're set up to do the Vinegar reaction. So let's take our alkyl halide, react it in triphenylphosphine, refluxed in toluene. And in the second step, we can bring in our carbonyl, which we can now call compound 1. We need a strong base like N-butyl lithium to form our ylide. And just like in the first step, we need an aprotic solvent.